Good morning all. So today's topic is thermodynamic potentials and Maxwell's equations. First let us derive thermodynamic potentials. Then after Maxwell equations, let us go for a simple trick through which we can remember Maxwell's equations easily. Okay. So we are having 4 thermodynamic potentials. The first one is internal energy. Internal energy. Okay. When system passes from one state to another state, the change in internal energy does not depend upon the path followed, but depends upon the initial and final states. For complete cycle, the change in internal energy is 0, and that change in internal energy can be written as du is equal to dq minus dw. Right? Now here, from first law of thermodynamics, dq equal to du plus dw. From that only we wrote it as du equal to dq minus dw. Now next, here dq means from second law of thermodynamics. dq means TdS, and the external work done value will be equal to PdV, pressure into change in volume. Substituting these values, du equal to TdS minus PdV. Okay, this is the first thermodynamic potential. Okay, now next let us go for the second thermodynamic potential, that is Helmholtz function. Helmholtz function. Right? From the first and second law of thermodynamics, we wrote du equal to TdS minus PdV. Right? From this equation I am writing du minus TdS is equal to minus PdV, or du minus TS is equal to minus P dV. Right? And now next here, this is written as dF equal to minus PdV, where F is equal to U minus TS. We call it as Helmholtz function. Right? Now differentiating it, we get dF equal to du minus, using the relation uv dash, we write it as v u dash minus u v dash. So s dt minus t ds, or df equal to du minus s dt minus tds. But let it be equation 1. From 1, du means what? TdS minus PdV. Now write this minus s dt minus tds. So now TdS minus TdS strikes off, df equal to minus PdV minus s dt. This is the second thermodynamic potential. Right? Now next, let us move for the third thermodynamic potential, enthalpy. Okay? Now next, let us move for enthalpy. Now here, enthalpy, it is expressed as H equal to U plus PV. Right? Now differentiating this equation, we get dH is equal to du plus, we are using UV method. So U V dash plus V U dash, we get PdV plus VdP. Okay. sorry, here also v u dash plus u v dash. So we will get du minus s dt plus tds. So du minus s dt minus tds. Okay, so here we get df equal to minus pdv minus s dt. And now dh is equal to du plus pdv plus vdp. Alright, now next step, here from the definition of enthalpy, H equal to U plus PV, we got du plus pdv plus vdp. Now let us substitute the value of du, tds minus pdv plus pdv plus vdp. So plus vdp minus vdp strikes off, dh is equal to tds plus vdp. This is the third thermodynamic potential. Okay, now next let us go for fourth thermodynamic potential, Gibbs function. Okay, and now here in Gibbs function, now from the definition of enthalpy, H equal to U plus PV we got. Now differentiating this, we get dH is equal to du plus pdv plus vdp, right? Now substituting du value, tds minus pdv plus vdp. So totally we got dH is equal to tds plus vdp, right? Now from this equation I am writing dH minus tds is equal to vdp, or d of h minus ts is equal to vdp, or I will write it as tg is equal to vdp, where g is equal to h minus ts, we call it as Gibbs function, right? Now let us differentiate this Gibbs function, h minus ts. Okay, we got h minus ts. Now differentiating g is equal to h minus ts. So we get dg is equal to dh minus tds plus sdt. Okay, now next dh minus tds minus sdt, that is equal to, now dh value is nothing but tds plus vdp from the above equation, the third thermodynamic potential, enthalpy, okay, minus tds minus sdt. So tds strikes off. So the fourth thermodynamic potential, Gibbs function value is vdp minus sdt. Okay, we got it as vdp minus sdt, right? And now here we got four thermodynamic potentials. Now by using these four thermodynamic potential, we have to derive Maxwell's equations. Okay, so for that let us derive an equation. Okay, Maxwell's equations, just a general relation for deriving the Maxwell equations. Now a mathematical theorem, I am writing z as a function of x comma v. Now doing partial differentiation, I get dz is equal to dou z by dou x at y dx plus dou z by dou y at x dy, right? Now in place of dou z by dou x At y I am placing m, and dou z by dou y. At x I am placing n, right? So now the equation turns out to be dz equal to m dx plus n dy. Let it be equation 1. Okay. Now next, let us do the partial differentiation. The partial differentiation of m with respect to y, right, and n with respect to x. Now we get dou m by dou y. M with respect to y we said, okay, dou m by dou y, we can write it as dou by dou y. But what is m value? M value, it is dou z by dou x. So we will get dou square z by dou y dou x. Similarly, differentiating n with respect to x, we get dou by dou x. Now n what we wrote? Dou z by dou y, right? Dou z by dou y. So we get dou square y by dou y dou z. As z is a perfect differentiable, we can write dou square z by dou y dou x is equal to dou square z by dou x dou y. Okay, dou x dou y. And now from this we can write dou m by dou y at x is equal to dou n by dou x at y, right? Now let us take the first thermodynamic potential. So from that we will get Maxwell's first relation. What is the first thermodynamic potential? Internal energy du equal to TdS minus PdV. Internal energy du equal to TdS minus PdV, right? Now first let us compare this with dz is equal to m dx plus n dy. So in place of m we are having t, in place of x s, in place of n minus p, in place of y v. Now substitute this in dou m by dou y at x is equal to dou n by dou x at y. So dou p by dou v at s is equal to dou minus p by dou s at, and what is y? V. Okay, so dou t by dou v at s is equal to minus dou p by dou s at v. This is the Maxwell's first relation. Okay, Maxwell's first relation. In a similar manner, let us derive Maxwell's second relation from second thermodynamic potential. Okay, Maxwell's second relation. So the second thermodynamic potential is Helmholtz function dF equal to minus s dt minus p dv, right? Now first let us compare this equation with dz is equal to m dx plus n dy. So in place of m we are having minus s, in place of x we are having t, in place of n we are having minus p, in place of y we are having v. Now let us substitute this in dou n by dou x at y equal to dou m by dou y at x. So what is n? Minus p. So dou p by what is x? T. And what is y? V is equal to what is m? Minus s. minus dou S by what is Y? V. Dou V at what is X? T. Minus minus cancels, so dou P by dou T at V equal to dou S by dou V at T. So this is Maxwell's second relation. Now similarly, let us go for Maxwell's third relation. Right? So what is the third thermodynamic potential? It is enthalpy. Okay, it is enthalpy, and enthalpy is written as dH is equal to TdS plus VdP. Right? Enthalpy is written as dH is equal to TdS plus VdP. Right? Now as usual, first let us compare with dz is equal to m dx plus n dy. So in place of m I am having t, in place of x s, in place of n v, in place of y p. Okay, so in such a way we compared. Right? Now next what I will do, I will substitute in dou n by dou x at y equal to dou m by dou y at x. So what is n? V. What is x? Yes. What is y? P. Right? So dou v by dou s at p equal to what is m? T. What is y? P. And what is x? S. Dou t by dou p at s. So this is Maxwell's third relation. Similarly, let us derive Maxwell's fourth relation. What is the fourth thermodynamic potential? It is Gibbs function. And what is the Gibbs function? dG. It is equal to VdP minus S dt. Right? Now first let us compare this with dz is equal to m dx plus n dy. So in place of m we are having v, in place of x we are having p, in place of n we are having minus s, in place of y we are having t. Now next what we will do, we will substitute in dou n by dou x at y is equal to dou m by dou y at x. So that is dou minus s by dou p at t is equal to dou v by dou t at x. X value is p. So this is Maxwell's fourth relation. In such a way we derive Maxwell's relation. Now what I said, let us go for a simple trick through which we can remember Maxwell equation. By hearting Maxwell equation we cannot remember Maxwell equations by hearting them. So we need a simple trick, a small trick to remember or get Maxwell's equation. So now let us go for the trick. The trick to remember Maxwell's equation. Okay. So now here we are having four thermodynamic potentials. One is internal energy du is equal to TdS minus PdV. So here in a systematic way you remember four thermodynamic potentials. It is easy to remember thermodynamic potential. After this you just write it as TdS is equal to minus PdV. Right? Now first take this dou t, right, divided by, and here dV is there, no, bring in denominator place as dou v. Okay, and as constant you write this entropy S, that is equal to, again you write minus dou p by this ds is there, no, you bring in denominator place, and then this V you write it as constant. Dou T by dou V at S is equal to minus dou P by dou S at V. Now let us see, is it correct or not, right? So what is the Maxwell's first relation? Dou T by dou V at S is equal to minus dou P by dou S at V. So that only we got, no? Okay. Now let us write the second Maxwell relation. Okay. So second thermodynamic potential, it is Helmholtz function, dF equal to minus P dV minus S dt. So first what you will do? We will write it as minus P dV equal to minus S dt. So minus cancels. So P dV is equal to S dt. Right? P dV is equal to S dt we got. Okay. Now what I will do? Here first dou P divided by equal to, and here dou S divided by. Now this dou T I will bring as denominator under it, and this dou V I will take as denominator under dou S, right? And then what I will do, here as constant I will write V, here as constant I will write T. So is it easy or not? Now next, the third thermodynamic potential, it is enthalpy. dH is equal to TdS plus VdP. Okay, TdS plus VdP. Now what we will write? TdS is equal to VdP. Now what we will write? First dou T in between equal to dou V. Now I will bring dou P under this, and this dou S under dou V, and then here S, here P. Okay, similarly the fourth thermodynamic potential is Gibbs function. So Gibbs function dG is equal to VdP minus S dt. So first you write it as VdP equal to minus S dt. So dou V by equal to, minus is there, no, minus dou S by. Now dou T, dou P, and then P and T. So in such a way, if we can remember the thermodynamic potentials in a systematic way, then easily we can write Maxwell's equation. So no need of by hearting the Maxwell equations, no need of memorizing or just going for a lot of practice to remember them. So if you know the four thermodynamic potentials perfectly, then by using such a small trick you can write Maxwell's equation wherever needed. Thank you.